this video, we're going to solve a problem that fits into Learning Goal CM.5, in which you combine conservation of momentum and conservation of energy in the same problem. It's not like the elastic collisions that you saw in CM3, where you're applying conservation of momentum and kinetic energy to the same collision. In these questions, you've got two stages to the problem. One stage is solved by conservation of momentum, the other stage is solved by conservation of energy. So you do them sequentially and solve the problem that way. So we're looking at this one, a skier sliding down a hill first. And then he'll be on level ground. There, level ground. So he starts up here. We'll call that position A. And his speed here is 0, and he's at a height of 25 meters. Okay, so he slides down the hill, and then he gets to the bottom. And he continues along the bottom where he meets another skier. And this skier has a speed of 0 initially, but not after the first one hits him. They continue on together in a completely inelastic collision. Now, as you recall, a completely inelastic collision means that the two all these things getting in our way. There we go. Our two skiers will be combined into one. So they are stuck to each other, their skis intertwined, and they move off as a single body with some speed, and that's what we have to solve for. So you probably recognize the first stage of this as a conservation of energy problem. It's a pretty simple one, actually, because we're neglecting friction. We just have gravitational potential energy converted to kinetic energy. So down here, H equals 0, V equals we don't know what. So that's a problem you know how to solve. That's a conservation of energy part of it. Then you've got this skier colliding with another skier. Collisions are conservation of momentum problems. And so we'll solve the conservation of momentum problem after that. So from A to B, we'll conserve energy. This means, of course, we need our LOL diagrams. So our system consists of the skier and the earth. And we are considering gravitational potential energy and kinetic energy. Initially, all the energy is gravitational potential energy. But at the bottom of the hill, that's all been converted to kinetic energy. So your energy equation, if the total energy at A is equal to the total energy at B, well, at A it's gravitational potential energy, at B it's kinetic energy. So mgHa equals 1/2 mvb squared. Our m's cancel and we can solve for the speed. (22.1 meters per second). I'm keeping the extra significant digit because I'm going to use that again. Okay. So now we know how fast he's going down here. All right, so we've solved for VB, and we're going to let that be well, we have to tell these people apart. Okay, if this is person 1 and this is person 2, then V1 is 22.1 meters per second and V2 is 0. What's that guy's mass? 72 kilograms. I'm going to write that down. Okay, and then they're going to move off together. Remember, they've joined together as one thing, and we will call their velocity together after the collision V12 prime. 1, 2 because they're together, and prime because it's after the collision. And let's call this point C, so that I can say that from B to C we will conserve momentum. So this is pretty simple as collisions go. It's one-dimensional inelastic, and you can't get much simpler than that. So the momentum has to be the same before and after. So M1 V1, the first guy, M2 V2 is equal to, well, they join together after the collision, so we can put their masses together. The total mass times their common speed. And we know that V2 is 0. The original guy was at rest. So we've got 66 kilograms, and we solved that his speed at the bottom of the hill at the beginning of the collision was 22.1 meters per second. Afterwards, the total mass times their velocity as they go off together. And you solve that, and you find out that they're moving at 11 meters per second. Okay, so to recap here, these types of problems involve conservation of energy and conservation of momentum in separate stages of the problem. You will need to draw a good system diagram with things labeled because there's a lot to keep track of. And then in one stage of the problem, you'll be conserving energy. In another stage, you'll be conserving momentum, and it won't necessarily be in this order from problem to problem, but it will allow you to go from what you are given to what you need to know. Now, your textbook doesn't have a separate section for this type of question. This was in your one-dimensional collision section. There was this, and there was the problem after it, which was a ballistics pendulum, which you weren't assigned, but you might want to have a look at. Mainly the problems for this learning goal are on the problem set that you were handed out. So that's how it works. Good luck.